Okay, class. Today I'm going to do a supplemental lecture from Lecture 12 on fluid statics. This is a detailed derivation of the fluid static equation. I went over the basics of this equation in class, but here I'm going to present the full algebra in case you would like. You don't necessarily need this if you can follow it in the book or if you can piece together the basics from what I said. But let me just give you the reference to the book. So this will parallel the derivation in Dean's book in section 4.2 on pages 85 to 87. Okay, so let's think about this derivation for a minute. So I drew this in class. So I have a cup of liquid here, and I'm going to take some chunk out of that liquid, okay, and I'm going to pull it out here. And so I want my derivation to be good for this whole fluid, but I'm going to take just a differential slice and I'm going to derive a differential balance. And so this is where our continuum approximation comes in, because I'm going to consider something that's differential. And that, of course, that differential piece needs to have many molecules for this to be valid. Okay, so if I come over here and I draw my rectangular prism, I've got, let me see while I draw, not the best at drawing on a computer. Okay, so this rectangular prism, and I'm going to set up a coordinate system. X, Y, Z. So this will be the X direction, this will be the Y direction, this will be the Z direction. I need that to be so to have a right-handed coordinate system. I'm going to find my gravitational constant in the down negative Z direction. So in other words, G is minus G in the Z direction. Or another way to write that is to write 0, 0 minus G in the vector notation we used earlier. Okay, and I'm just going to label a couple of these points. So note that, this is the y direction, so that means that I have the y unit vector on that side, but on this side over here, the outward normal is minus EY. Okay, and this would be EX, and then the back would be minus EX, etc. I'm going to call this point in my coordinate system, I'm going to call that the XYZ. So let's see, I don't really have space. I'm going to draw a little arrow out here, and I'm going to call that XYZ. I'm going to call the length of each of these sides a little delta. So this is the X direction this way, so I'm going to call that direction delta X. The Y direction is here, that one is delta Y. And the Z direction right here, so I'm going to call that one delta Z. Which means that if I go X and I go up here, then this point will be X, Y, Z plus delta Z. Okay, and then if I go in this direction over here, this one will now be, this is starting to get kind of messy, but X, Y plus delta Y, Z. Okay, and this guy over here will be X plus delta X, Y, Z. Okay? So I have this rectangular prism, I've defined a coordinate system, I've defined some points. We're going to use this to do our force balance. Okay, so that's now what we're going to do, is we're going to set up a force balance. So force balance on the rectangular prism. Oops, rectangular prism. Rectangular prism. Okay, so remember I said that there are two types of terms. So there is force from pressure, okay, is one of the terms, on each side. Okay, and there are 6 sides. There's so let's go through and just write the force down. Force is minus N times the pressure times the area. So I scroll down a little bit here. So now the different n, those are going to be plus or minus in the x direction, plus or minus the unit vectors in the y direction, plus or minus the vectors in the z direction. So those are the 6 sides, okay? And then I'm going to have my pressure, which is a function of space here, okay? So I'll have p, x, y, z, okay? And I could move around, and so x, y, and z can get changed. And then my area are going to be the area of these faces. So the area will be something like delta y times delta z, or delta x times delta y, something like that. Okay, I'll do these out in detail. I'm just trying to sort of preview what's going to happen. So that's one type of force. The second force is the weight of the fluid. Okay, and the weight of the fluid is F equals mg, where g is this g minus GeZ. Okay, so now that I've written down what I'm going to do, now I'm going to do it. So this is our force balance. I have the sum over all the forces is 0. Why is it 0? Because it's a static fluid. If the fluid were moving, that wouldn't be 0. We would have, F equals ma. We'd have to worry about, and we're going to do that in a couple of lectures. All right, so now I need the forces. So let me get the forces on the different faces. So I'm going to have 6 of these, and then I have a weight of the fluid that I'm going to have to add up. So the first one I'm going to do is the positive EX direction. So that's the one on the front. So the unit normal is facing towards us, right, towards me out of the page, okay? And so here I'm going to just write down F equals minus NPA, and that is a minus EX. And then the pressure, and I have to be a little careful about the pressure. If I look up here, the pressure is out here on this face, which has a plus delta X in it. Okay, so I'm out on that whole face, and I have a plus delta X. So I'm at the pressure of X plus delta X, Y, Z. Then I need to multiply by the area. Well, what's the area on this face? Well, here is a delta Y, and there is a delta Z along there. So this one has delta Y, delta Z. Okay, so that comes over here, delta Y, delta Z. Okay, so that's one side. Okay, now I have another side. So this will be the minus EX direction. Okay, and I'm going to draw the face here. It looks just like our other face before, but now the normal vector is going backwards, which is minus EX. Okay, so now I want you to pause the video for a second and see if you can write down what the force is here and test yourself and see if you understand what's going on. Okay, so if you paused and test yourself, great. So let's write it down. We have minus, and now we have a minus EX. So now the normal vector is backwards. Okay, it's now going the opposite direction, which, oh, where's my camera? Right there. Okay, in that direction. Okay, and the pressure is only at X, Y, Z instead of X plus delta X, because look back up here at our thing right there, okay? It's back along that face, which is at X, Y, Z, okay, instead of at X plus delta X. Okay, but I have the same area. I have an area of delta Y, delta Z. So I have to put that in here, delta Y, delta Z. Okay, I'm going to do one more of these in detail, and then I'm going to write the other ones down so we don't kill ourselves forever. So EY, okay, EY is one of these sideways facing ones with the normal vector now in the Y direction. All right, and then we can come back up here and look, and I have delta X in this direction and delta Z in this direction, so that's going to be for my area. And look, I'm at X and Y plus delta Y. So here I have a delta X and a delta Z, and I'm at X, Y plus delta Y, Z. So now when I write down the force as minus N pressure times the area, this becomes minus EY P of X Y plus delta Y Z delta X delta Z. Okay? And now I'm going to write more quickly, okay, the minus EY, it follows a similar pattern. So if I write down minus EY without drawing it, I'm going to get the force is minus NPA, which is minus EY, P of X, Y, Z, delta X, delta Z. Okay, and what pattern does that follow? So look, just like when I went from the positive EX, I had X plus delta X, and here I just had X. Here I had Y plus delta Y, and in the negative Y direction I just have Y. And then I have a negative sign flipped between the two, which is just the same here. And then they have, oop, I drew a little something down there. Let me erase that real quick. Oop. Okay, and here I have delta Y, delta Z, delta Y, delta Z. Here I have delta X, delta Z, delta X, delta Z. Okay, so now I can write the last two in the Z direction. So in the Z direction, force is minus NPA equals minus EZ P of X, Y, Z plus delta Z, delta X, delta Y. Do you see the pattern here? Same as this one, okay? Analogous, EY, EZ. This has the Z plus delta Z, and now my area doesn't include the delta Z term. Okay, and when I have a minus EZ, I get the force is minus N pressure area, which is minus a negative EZ, P of X, Y, Z, delta X, delta Y. Okay, so those are the 6 faces. The last force that I have is the gravitational force. Okay, gravitational force is the mass times gravity of this whole box. Okay, because these are called surface forces. Okay, for reasons that we just saw, they act on the surface. This weight here, this is called a body force. It acts on the entire body. So now I need to get the weight of the fluid. So I'm going to just make a little note of that down here. Weight. Okay, so this is F equals mg. Okay, which I said was minus mg ez. So we can have it in this notation. But m, I want to know a little more about m. Let me expand that. That is the same as minus rho times the volume times g ez. And what is my volume? I can rewrite that as minus rho delta x delta y delta z g ez. Okay? Now I have everything I need to do. Right? Phew. Okay? Long. See why I didn't want to do it in class? Okay? Let's write it all down together in one place. And maybe we'll just write it out. Okay? So I'm going to write, I have minus EX P, let me just scroll up a little bit so I can see here. Minus EX P X plus delta X, X plus delta X, Y, Z times delta Y delta Z minus a negative EX of P of X Y Z delta Y delta Z minus, and now I can start copying, right? Did my parentheses and my P backwards. Minus EY P of X Y plus delta Y Z. Okay, that should be this guy right there. Oh, I already had it in my screen. This one right up here. Minus EY P X Y plus delta Y delta Z, which should have a delta X delta Z. Plus EY P X Y Z delta X delta Z. Now I need my Z terms. Minus EZ p at x, y, z plus delta z of delta x delta y plus ez p, oh man, I did it again. Oop, there we go. P of x, y, z, delta x, delta y. And finally, I have this guy, minus rho g, delta x, delta y, delta z, ez equals 0. So the sum of my 7 forces, 0. Okay, now, done with the sum of the forces. Now I'm going to do the following. I'm going to rearrange this equation a bit. I'm going to first divide by the volume, which is delta x, delta y, delta z. Okay? So I'm going to divide by the volume. So look at what happens here. That's going to go away. And this here, delta y, delta z, I'm going to be left with a 1 over delta x. 1 over delta x. And this line, right, so here I'm going to have a 1 over delta x left. This line I'm going to have a 1 over delta y left. And this line I'm going to have a 1 over delta z left. Because here, if I have delta x, delta y, I divide by delta x, delta y, delta z, I have a 1 over delta z. Okay? So let's write that down. So I now have minus ex of p of x plus delta x, y, z. And I'm going to put my minus ex out. I'm going to put a bracket here. And that will mean this will have a minus sign because I pulled a negative out of x, y, z, bracket, divided by delta x. Minus ey of p of x, y plus delta y. Oops, forgot my z. Delta y, z, minus p of x, y, z, divided by delta y. One more, minus ez of p of x, y, z plus delta z, minus p of x, y, z, divided by delta z, minus rho g ez equals 0. Okay? Okay, we did that. Now, let's look here. I've got p of x plus delta x minus px divided by delta x. And something y plus delta y divided by delta y. Z plus delta z minus z divided by delta z. That looks a lot like a derivative. Well, lo and behold, I am now going to take the limit as delta x goes to 0, delta y goes to 0, and delta z goes to 0. Alright, so when I do that, look what happens here. I have the limit as delta x goes to 0 of, say, p of x plus delta x, y, z, minus p of x, y, z, divided by delta x. That becomes dp dx, partial derivative of p with respect to x. So now I have, that will happen here, here, and here. Okay, nothing happens here, all the deltas went away, so that will just stay. So now let me rewrite. I'm going to leave that in the frame so we can see. So I get minus dp dx ex minus dp dy ey minus dp dz ez minus rho g ez equals 0. Hey, that's looking pretty awesome. I got a lot simpler. Well, let me write down. I have 3 equations. I have minus dp dx equals 0. Minus sign goes away. That doesn't matter. I have dp dy equals 0. And I have dp dz equals minus rho g. Okay? Because this 0, of course, is vector 0. Or another way to write this, if I look at this, what is something where I have a derivative with respect to x, ex, plus a derivative with respect to y, ey, plus a derivative with respect to z, ez? What is that? That's a gradient. So another way of writing this is I have minus gradient of p minus rho g ez equals 0. But I said that minus, I said up here at the top that g was equal to minus g, minus not the, where did that go? There it went. Erase. There you go. Minus g ez. So I can rewrite this right there as minus grad p plus rho g vector equals 0. Now that's all in vector notation, and we get to our very short form of the static pressure equation. If I rearrange, which is just grad p equals rho g. Boom. That's the static pressure equation. All right, so what does that mean? Okay, that means these three equations. Same thing. Okay, it means it's a vector equation, so it's really three equations. So it says there's no pressure gradient in the x direction, there's no pressure gradient in the y direction, and there's a pressure gradient that's equal to minus rho g in the z direction. All right? This, what we just did, okay, this is called a differential force balance. This is a differential force balance. All right. It's also sometimes called shell balance. Shell balances are slightly different in the way that they're sometimes derived because they use shells to take account for what's coming in and out. So we used this whole little cube, but you can write it as a little cubic shell, and that probably isn't super meaningful to you, but you might see shell balances later. But this is a differential force balance. This is the one way to come up with the static pressure equation and other equations, and we will see several other examples of differential balances. Okay, this is how we will get the Navier-Stokes equation. As a matter of fact, the Navier-Stokes equation will be the force balance when we add in the mass and acceleration terms. Okay, so when we go back to this guy up here and we add stuff back in on this side, that's how we're going to get the Navier-Stokes equation. Okay, I think that's all I have. Hope that was useful.